So our next lesson in chapter 9 is called the altitude on hypotenuse theorem. Sorry. We are skipping 9.2, so that deals a lot with circles, which we're going to do a whole chapter on in chapter 10. So we're just going right on to 9.3. Now this new theorem is actually, it's called a theorem, but it's actually like a formula, and it helps us find side lengths. This is going to be very new. So these notes are going to go a little bit different. I do want to show you and go through the process of where the formula comes from, but that's not something that you're necessarily going to be tested on. You're going to just have to know how to use that formula. So the beginning here, I'll kind of go through some parts that maybe you don't have to write in your notes, but it's good for you to see. So I'll kind of let you know which things you need to write down and which things you don't. So here we go, 9.3, altitude on hypotenuse theorem. So just kind of a review. This is not something you would necessarily have to write down. This is just a review. What an altitude is, because this is called the altitude on hypotenuse theorem, right? So we're going to review what is an altitude and what is a hypotenuse, right? So altitude, again, is drawn from a vertex to the opposite side and is perpendicular to that opposite side, right? And the hypotenuse is the longest side of the right triangle, or the side across from the right angle. So if we're going to use the altitude on hypotenuse theorem, we have to have some certain things in our picture, right? So these are things maybe you would want to write down. So write down altitude on hypotenuse theorem, right? Things you have to have. You must start out with a right angle in your picture. So you have to have this right angle up here in your picture. So you have to start with a right triangle. And then you're going to have an altitude that comes from that right angle and is drawn to the hypotenuse. So again, an altitude makes right angles with that opposite side, right? So the altitude must originate from the right angle and be drawn to the hypotenuse, okay? So you're going to have your right angles down here. That altitude is going to connect to the hypotenuse, the side across from the right angle. Notice when you look at this picture, I really have two different sets of right angles, right? The original green one up here from our right triangle to start with, and then the new right angles down at the bottom when I draw it to the hypotenuse. So that's the idea. That's what your picture has to look like if you are going to use this new theorem that I'm going to show you in a minute, okay? So when we do that, when we get a picture that looks like this, that is when we're going to have a setup for the altitude on hypotenuse. Now, what I'm going to do on this slide is I'm going to show you where the theorem or the formula comes from. This is not something you would need to write down. I just want you to kind of see how it happens and where it comes from, okay? So as you see, this is in the part that I highlighted in yellow up at the top. That's when we just set up our altitude on hypotenuse theorem, right? We had our right triangle to start with. We drew an altitude going to the hypotenuse. Now, if you notice, as we did that, we kind of broke it into three different triangles, right? The original big triangle, this triangle on the left, and this triangle on the right. Now, all three of those triangles are right triangles, and in fact, they're similar. So I'm going to move over here now to this one on the left. Whoops. Okay. So if I look at the whole big triangle, the big original triangle, right triangle, and then the triangle on the left, this one over here, right? So if I looked at my big picture, again, this was the original, and then the triangle on the left. These two triangles are similar by angle-angle similarity because they share angle A, right? So our right angles are congruent, and then they share angle A, reflexive property. So now I have angle-angle similarity, right? And if you line up the corresponding parts, it's triangle ABC, similar to triangle ACD. So when I have similar triangles, like we learned in chapter 8, I have all kinds of, not all kinds, but three pairs of sides that are corresponding, that the ratio of sides is the same, right? So I have this, my hypotenuse of this one, AB, over the hypotenuse of this one, AC, right? That ratio of sides will be the same as the ratio of BC to CD, right? Those are the corresponding parts, BC over CD. And the ratio is also the same as the bottom here, AC over AD. Now you could find those ratios of sides just by looking at the order of the letters, right? AB to AC, BC to CD, AC to AD. Okay, so we know that all three of those ratios of sides is the same, right? They're not congruent, even though I marked them that way. I just wanted you to see which ones line up and correspond. Now, the thing is, we know this. We did that in chapter 8, but what I want you to pay attention to right now is there's a couple of interesting things. If you notice this first ratio and this last ratio, they both have segment AC in them. So if I just rewrite just those two, that would say AB over AC equals AC, oops, I wrote it wrong down in here on the bottom, I apologize, over AD. Now, I know that when I have a proportion like this, I can cross multiply. So if I cross multiply like this, oh, AC times AC, that's AC squared, equals AB times AD. That's part of the altitude on hypotenuse theorem. That's part of a formula. That's one of the formulas. Now, if you go back to our original picture, AC is this segment right here, right? So this segment squared equals AB, this whole hypotenuse, times AD, the part closest to it. There's one of the formulas. All right, now I'm going to leave that one alone for now, and I'm going to come over here to this one, the green one on the right, okay? So same kind of idea, right? Now I'm looking at, again, my big triangle and my triangle on the right. So big triangle, now this one. And again, those ones, like very similarly, are, excuse me, are similar because they share angle B. So my right angles are congruent, and they both share angle B, which means they're similar by angle-angle similarity. And then I can line up all my corresponding sides, right? Same way. So I could take a look at my letters, right? AB over CB equals CB over DB equals AC over CD. Now again, we're looking through here and trying to find the two ratios that have the same segment in them. So in this case now it's the first two. So if I just look at those two, I have AB over CB equals CB over DB. And if I cross multiply, I get CB squared equals AB times DB. There's the next part of our formula. So if I look back at my original picture here, CB squared, that's this segment. So that segment squared equals, AB is the whole thing again, just like last time, times BD, which is just this first part. Do you see something similar, right? When I went down the left side squared was the whole hypotenuse times the left part. And now I went down the right side, and the right side squared equals the whole hypotenuse times the right part. So the last pair of similar triangles we have is not the whole triangle this time, but the left little triangle compared to the right little triangle. Now, if the left one is similar to the big one and the right one is similar to the big one, then the left one must be similar to the right one. So that's what we mean by the transitive property. But same idea, right? So I can come up with all of these ratios again. So if I come up with my ratios again, AC over CB equals CD over BD equals AD over CD. And if I look for the two that are the same, we're running out of space here. They're right here, right? So I have, I'm going to move up here. Oops. Here I go. Okay. CD over BD equals AD over CD. So if I cross multiply, I would get CD squared equals BD times AD. There's the last part of our formula. CD this time, that's the altitude. So the altitude squared equals the right side times the left side. Okay, so that's 3 different formulas, and they all come from similar triangles. But again, you don't have to have this written down. I just wanted you to see where it comes from, because really, all that I want you to remember are those formulas about which side squared, and then part times whole, or whatever that is. So a lot of people get kind of confused. So here's where we're going to really just solidify the things that you need to remember. So what I have is there's 3 different formulas, right? And there's a great way to remember these 3 formulas, and that's by using skydiver. So you're probably like, what? Skydiver? Picture, do you kind of see this picture? I see it, it's the same thing drawn 3 times. This picture looks like a mountain, right? So if we picture, a skydiver, landing on top of this mountain, right? With his parachute. That's a parachute. So he lands on top of the mountain, right? He's got to come down the mountain somehow. So if I'm going to slide down, oh, I apologize. I have these weird letters. Okay, so parachute man is sliding straight down the altitude. Let's say he comes down the middle, all right? So if he comes down the middle, he's going to land at the bottom, but it's hard coming down the mountain, right? The way down the mountain is tough, so that's why we're going to square it. So altitude squared equals. So he lands down here at D, right? Where could he walk? Well, he could walk left, or he could walk right, but he can't magically teleport and start over here at A and walk the whole thing, right? He can't do that. He's got to start at D. So he could walk segment 1, or he could walk segment 2, and those are the things that I multiply together. So whichever way you come down the mountain, you square it, and then whatever places he could walk to, you multiply. And that's the first formula for altitude on hypotenuse, our skydiver. Okay, so what's another one? Okay, so let's say he comes down leg 1. So here he is at the top of the mountain again, right? This time, he could come down this left-hand side, leg 1. Remember, hard coming down the mountain, so you're going to square it. So leg 1 squared equals. He's going to land here at A. Where could he walk to? Well, he could walk just segment 1 and stop at D. Or he could walk the whole hypotenuse and land over here at B, but he can't magically teleport and only walk segment 2. That's not going to work. He's got to start at A, right? So leg 1 squared equals segment 1 times the whole hypotenuse. But he can't do segment 2. All right, so then our last option here, he is at the top of the mountain, right? This time he's going to slide down leg 2. So he's going to start down, and he's going to go down the mountain this way, right? So whichever way he comes down the mountain, you got to square it because it's hard work. So we have leg 2 squared equals. He's going to land here at B. Where could he walk? Well, he could walk just to D and end there. That's segment 2. Or he could start at B and he could walk the whole hypotenuse, but he can't magically teleport and only walk this little segment over here. That's not going to work. So leg 2 squared equals segment 2, or the part closest to him, times the whole hypotenuse. And those are the 3 altitude on hypotenuse theorems. Those are the formulas you need to remember. Now, please notice, in all 3 of these pictures, there is that right angle up on top. That's where the skydiver is starting, right? So he always has to start from the top of the mountain, and you'll know it's the top of the mountain because there's snow on top. That's the key. Must have snow on top of the mountain. That snow is your right angle, right? So it's got to have that right angle on the top of the mountain. That's where he starts, and that's where your formulas all start from. Whichever way he comes down the mountain, you square it, And then you set it equal, and wherever he can walk to without teleporting, that's what you multiply together. All right, so hopefully you have this written on in your notes. You definitely need these 3 different pictures and your 3 different formulas written in your notes. This is the altitude on hypotenuse theorem. Okay, so now we're just going to practice using it. So again, you're going to see these pictures, right? This is the standard setup for altitude on hypotenuse. Here we've got our snow on the top of the mountain, right? We've got our right angle down below. So I know that I have altitude on hypotenuse. So you picture, okay, where's my skydiver starting? He's starting up here with the snow on the top of the mountain. So in this problem, it says AD is 3, DB is 9, and I'm finding CD. And it's all marked with us, X in the right spot and everything. So, okay, I'm trying to find X. That means this is the way I'm coming down the mountain, right? So whichever way I come down the mountain, I've got to square it. So X squared equals. I land here at D. Where could I walk? I could walk left, 3, or I could walk right, 9. So I multiply them together. X squared equals 3 times 9. So X squared equals 27. I'm going to square root both sides. Now here's the tricky part. Remember, we reviewed this yesterday. So when I have the square root of 27, is that a perfect square? No. So I'm not gonna get a decimal or anything. I'm gonna simplify that radical. So that breaks into the square root of 9 times the square root of 3. 9 is a perfect square. So I have 3 radical 3. But I created that square root sign in order to solve this problem. So it should really be plus or minus 3 radical 3. So that's going to be in my work because otherwise I will forget to write that plus or minus if I need it. But hang on, what is X? X is this segment length in my picture, right? So can a segment length be negative? It can't. So I'm going to cross it off, but it should still be in my work. So my final answer here is X equals 3 radical 3. That's how you use the skydiver to solve a problem. All right, take a look at the next one. See what you can do. Same setup. This time I'm finding AC, right? AD is still 3, DB is still 9, but this time I want to come down this way, right? So I'm going down that leg this time, so that's still squared. X squared equals. Now, where could I walk? I could walk the short route here and just do 3. Or I could walk the whole thing, right? I can't teleport and just do the 9 like I could last time. That doesn't work because I landed at A. So this time I have to do the whole thing. Well, if the first part is 3 and the second part is 9, the whole thing is 12, right? So X squared equals 3 times 12 for this one. All right, X squared equals 3 times 12 is 36. Square root both sides. X equals, let's see, square root of 36, that's a perfect square, plus or minus 6. But it is still a side length, so negative doesn't make sense. So X equals 6 on this one. So be careful, right? Just because there's a 9 in the picture doesn't mean that that's something you're going to multiply by. You really got to make sure, am I multiplying by just that part or the whole thing? And how could you get it? So that's how you're using altitude on hypotenuse. All right, here's another one. Let's see. This time it says DB is 21, AC is 10. Find the length of AD. Still have our, excuse me guys, sorry. Snow on the top of the mountain. Right angle down below, so I definitely have skydiver. Skydiver lands up at the top of the mountain that has the snow on top. And which way is he coming down? Well, X is down at the bottom, but hopefully you're starting to get the feel of this. And you can see that it's kind of easy. I can see which route I'm going to come down because I have a 10 here, so that's the way I'm going to come down the mountain, right? But again, remember, whichever way you come down the mountain, you have to square it. So this is going to be 10 squared. Where could I walk now that I land down here at A? I could walk the short part, X. Or I could walk the whole thing, right? So I can't just walk the 21 because I can't teleport. Got to start at A and I could walk the whole thing. Well, if the first part is x and the second part is 21, the whole thing would be x plus 21, right? Not 21x, not x times 21. I have to add those two bits together. So I have to multiply x times x plus 21. I'm going to walk this first part, which is just x, or I'm going to walk the whole thing, which is x plus 21. Notice I put the x plus 21 in parentheses. I need to multiply x times that whole part, so I need to make sure I have my parentheses. All right, well, let's see. 10 squared is 100. I'm going to distribute here. X times x is x squared. X times 21, 21x. Oh, okay, think back to yesterday. How do I solve something like this? I have an x squared and an x. Can't use square roots, so I got to get it equal to 0 and factor. So I'm going to subtract 100 from both sides so I get it equal to 0. So I'll get x squared plus 21x minus 100 equals 0. All right. Now, if you need to use a factor box, you can. Remember, we reviewed this yesterday. If you can do this without the factor box, you can just go straight to your parentheses. That's totally fine, too. If you were going to use the factor box, it would be x squared here, negative 100 up there, 21x down in the middle. What multiplies together to give x squared? X times x, that's an easy one. What's going to multiply together to give negative 100 and add up to 21? Multiply together to give negative 100. That means one of them is positive and one of them is negative. So let's see. I'm thinking 25 times 4. One of them has to be negative, so I think it's going to be negative 4. When I multiply across here, x times 25 is 25x. X times negative 4, negative 4x. 25x plus negative 4x equals 21x. And then remember, it is my diagonals that go in my parentheses. So I'll have x plus 25 as one set, x minus 4 as my other set. All right, so let's see. Now I make my two mini equations. X plus 25 equals 0. Subtract 25 from both sides. X equals negative 25. And x minus 4 equals 0. Add 4 to both sides. X equals 4. Remember, you're showing all of your work here. It's easy to make a little mistake with our negatives. So my two possibilities here are negative 25 and 4. Do both of them make sense? Ooh, x is a side length, right? Can I have a negative side length? No, so this one doesn't make sense. But 4 would make sense, right? AD could be 4, DB could be 21. Sure, that makes sense. So AD is 4. Because we can't have negative side lengths. Now, if those were both positive numbers, and they both made sense, then you could possibly have two answers here, right? Whenever you end up with this quadratic equation situation where you have an x squared, there's a possibility that two different numbers would work, and that's totally fine. But you guys just got to check both of them to make sure that they make sense in the problem. All right, so same setup, a little bit trickier to solve, but still the similar idea, right? Okay, so here's our last one. This time they didn't mark any right angles in our picture, but notice the givens. The given says AD is perpendicular to CD. AD perpendicular to CD. Okay, so my right angle is right here. And then the next one says BD is perpendicular to AC. Aha. So here are my right angles down at the bottom. So I do have my altitude on hypotenuse situation. BC is 5, AD is 6. What am I trying to find? I'm trying to find BD. Okay. This one is not as straightforward, is it? So I see I have my altitude on hypotenuse. I've got my snow on the top of the mountain, which means my guy would land here. I have two different routes to come down, but neither of them have exactly what I need. If I come down the 6 that's there, I could walk AB, but that's missing, or the whole thing, right? Which I would have to add together. If I come down the altitude here, which is what I'm trying to find, BD, I could walk right, which is 5, or I could walk left, which again I don't have. Maybe I need a second variable. So maybe I'm going to put y in that part right there. And then I could possibly come up with 2 different equations in order to solve this. So let's see, if I have my y here, if I come down the 6, that means it would be 6 squared equals y, because I could walk the short part, times the whole thing. Oh, how much is the whole thing? First part is y, second part is 5. The whole thing would be y plus 5, right? Just like the last one that we did. So my first equation would be 6 squared equals y times y plus 5. Ooh, well, I could just go ahead and solve that for y, couldn't I? Okay, 6 squared is 36. Distribute, y times y is y squared. Y times 5 is 5y. Again, I have a y squared and a y, so I need to get it equal to 0 and factor. So I have y squared plus 5y minus 36, because I have to subtract 36 on both sides to get it equal to 0. All right, again, you could set up your factor box here, or if you're okay going straight to your 2 parentheses, I have to have things that multiply together to give me negative 36 and add together to give 5. Obviously, my first terms have to be y times y. 36. I'm thinking 9 and 4, right? 9 times 4 is 36. And if I have positive 9 and negative 4, that would give me negative 36. And it would add up to positive 5. Again, you can use your factor box to get those parentheses if you need to. That's perfectly fine. Okay. So now I take my 2 mini equations and set them each equal to 0. Y plus 9 equals 0. Subtract 9 on both sides. So I get y equals negative 9. Y minus 4 equals 0. Add 4 to both sides. So I get y equals 4. Check it out to see if both make sense. Ooh, y is an actual side length, so negative 9 is not going to make sense. So y must be 4. All right. Now that I know what y is, now I could set up an equation to come down the altitude here and solve for what I really wanted to, which was BD, right? So I'm solving for x now. So that means x squared equals, where could I walk? I could walk left, which was the 4 that I just figured out, right? So 4 times, I could walk right, which was 5. All right, x squared equals 4 times 5. 4 times 5 is 20. So I have x squared equals 20. Square root both sides. Ooh, 20 is not a perfect square. Square root of 4 times the square root of 5. X equals 4 is a perfect square. Square root of 4 is 2. So plus or minus 2 radical 5. But x is a side length, so negative doesn't make sense. So I'll cross off the negative. So x equals 2 radical 5. That is what BD equals. All right, so even if it's a little bit complicated, you can use that skydiver idea. You could use the skydiver idea more than once, right? Just depends on what you have and what you're trying to solve for.